Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, you know that in SolidWorks Flow simulation, homogeneous fluid mixing is possible in a specific fluid domain. In a single domain, heterogeneous fluid mixing is not possible through normal processes, and it can be done using some specific method known as free surface technique. It was introduced with the SolidWorks interface from 2017 onwards, right? So in free surface technique, what we have to do is we have to consider two different fluids in the same fluid domain, and we have to specify their volume also, right? Today in this video we'll show two different videos with different boundary conditions. First of all, we'll take this one. This is a container. Top part is filled up with air and the bottom part is filled up with water, and actually it is open from top end, and from the downside we have provided one opening. So due to gravitational action, water will come down. As water will come down, by the same time we'll see that volume fraction of air will be also increased. In the second analysis we'll show if the gravitational direction is changed. In that case, water will come down, by the same time air will go inside, right? So two different boundary conditions will be there in our videos. Let us start our first one. This is the model, and for making the model we have to consider one specific thing. That means we have to make this inner portion also solid. That means the water portion what we have provided, that should be also solid. It will be unmasked inside this container, right? So without wasting time, let's start our analysis. And the top part and bottom part we have already provided some kind of lids, so it is a closed geometry. We're starting from flow simulation, and the flow simulation environment will be created with the wizard itself. So we're starting from wizard, and default name of the project we're keeping as project 1. Next to that, we need to select unit system, and we're considering default unit system as SI, and from temperature we're considering centigrade, though in this case this temperature is not important part. Anyway, next to that we need to see what type of analysis it is. It is an internal analysis. We can do an external analysis also, but in that case it will take more time, so we're considering this one as an internal analysis. And from physical features it will be fluid flow, and you know that this is not a steady state condition, so at different times we will have different results. So it will be transient analysis. It is dependent on time. We're considering total time for this one to be 60 seconds, and output time we're considering as 0.1 second. That means after each 0.1 second we'll get the results, right? And gravitational action will be also there, and direction of gravity will be indicated by this green arrow in the upward direction. That means it will be y minus 9.81 along y direction, and along z it will be 0. And finally, free surface condition we have to check in, because it is a heterogeneous fluid mixing in a specific domain, in a single domain, so we need to consider free surface technique. Checked in. Next to that, we need to consider different fluids. It will be gases, and from gases we'll consider air, and from liquids we'll consider water. Both the fluids air and water is taken, and you can see here it is showing that default fluid type is immiscible mixture of water and air, right? Next to that, this default thermal wall conditions and roughness is not having that much of effect in this case, so we are considering default auto wall thermal conditions and roughness. And next to that, we need to consider the final thing, that means atmospheric pressure is 10135 Pascal, and temperature we're considering as 20 degrees centigrade, and concentration it will be air, because initially the top part is filled up with air, and the bottom part we have to adjust with the initial conditions. Bottom part is actually solid, that to be converted as liquid, right? So the top part what we have taken, this is considered as air. By default it is considered as air, and the bottom part we have to make this one as water, right? So let us finish this. You can see this is the computational domain, and top part is actually filled up with air, and the bottom part we have to consider this one as water. That can be done using conditions, initial conditions, and we need to select that bottom part. That can be selected from the solid geometry itself. This is the revolved 2 portion selected, and that to be disabled as solid components, and we have to consider this one as water. So we have defined that bottom portion is filled up with water and the top portion is filled up with air. By default, it is considered as air, and the bottom portion we have made this one as water. Green check. Next to that, we need to apply our boundary conditions. So insert boundary conditions. At the beginning, we were told that the top part is open and the bottom part we are having one opening, right? So we need to apply two boundary conditions at the two different locations. Let us rotate this one a little bit to apply actual boundary conditions. Before that, we can hide this fluid domain also. So computational domain, let us hide it. We need to apply our boundary conditions. So insert boundary conditions, and it will be atmospheric pressure at the top exit location as it is open. So select other, it is lead number 1, selected, green check. Exactly the same way you have to apply another boundary conditions at the bottom opening because it is exposed to atmospheric air. So for better selection, we can have either a segmented view of this model, or we can rotate this one a little bit to select in a different way. Let us rotate this model. So we need to apply the last boundary conditions. Insert boundary condition. It will be environmental pressure or atmospheric pressure at the bottom opening. Select other, it will be lead number 2, selected, green check. Both the boundary conditions are applied. Next to that, we need to select some goals. In this case, we can select some goals like mass fraction of water or air, or volume fraction of water or air we can consider, right? So we'll select from goals, insert global goals, and we need to select different fractions of water and air. It will be mass fractions or volume fraction of water and air, right? We can select this from here itself. It is average mass fraction of air and average mass fraction of water. By the same time, we can select volume fraction of air and volume fraction of water separately, right? All the goals are actually global goals. Green check. All the goals are defined. Before running this one, what we have to do is we need to mesh it in a better way. Global mesh, and we can go for manual meshing also. Display the refinement level. Refinement level is 1 only. For better refinement, we can go for up to 3, right? Done. Green check. Next to that, we need to do something else. That means from solve, we need to select calculation control options, and from here we need to select saving options, and we can select periodic transient explorer, and from here at the bottom right corner we can select pressure, temperature, different fluid parameters, and immiscible air, immiscible water, mass fraction of air, mass fraction of water, and also volume fraction of air and water we can select separately from here. That is having some advantages. That one will be shown later on. Okay, done. Now we can run it. We have already run these results with the same data, so we can view these results from project 2, right? Let us see the results from here itself. For running this one, it will take a lot of time, so to save the time, we have done this one before. We can view the results from project 2, right? Okay, first of all, what we'll do is we have to load the results from here itself, and we can change the orientation to front plane. Next to that, we need to see some cut plots, right? Here in this case, we are having a lot of other options that at different times, what will be the different mass fraction of water or volume fraction of water or air can be viewed. By the same time, you can see what will be the different heights of water and air at different times. That can be viewed very clearly, right? So initially, we will see some cut plots. Insert cut plots, and we will see mass fraction of water, and we're going to see contours and also mesh, By the same time, you can see some isolines also, or vectors. Let us see. This is the distribution. Now, one thing, very important thing, that means through Transient Explorer, we can see at different times what will be the different height of this water and air separately. It can be viewed very easily, right? So we can introduce this Transient Explorer from here itself. Transient Explorer, and we have run this one for 60 seconds, and at different times we can see the height of water and air separately, right? We can bring this one down a little bit. Now we can run this and see from Transient Explorer that at what time what will be the different fractions of water and air separately. You can see at 0 second it was there itself, and it is coming down as time is approaching. Water level is decreasing, by the same time air level is increasing as it is exposed to atmospheric air from the top side. So air will be entering inside this container, right? You can see here at 23.4 seconds, this is the level of water. That means water has come down to this much of level, and as top part is exposed to atmospheric air, so air will be entering at this location. So as water volume fraction will be decreasing, volume fraction of air will be increasing, right? You can see it again. Excluding this one, we can do something else, like with the XY plot we can see the height level, how much height is decreasing, that can be quantified by using that XY plot, right? So for that we have already made one line from the bottom to the top section, right? Let us introduce that XY plot. XY plot, insert, and we are considering only mass fraction of water. We can select different parameters also, but we are bothered about mass fraction of water only in this case. I need to select that line. This is the line is selected, and let us show this one. It is showing here itself mass fraction of water, or we can export this one to Excel also. Better we can check it from here itself and see how it is changing. Let us analyze this one, right? You can see when time is 4.2 seconds, in that case you can see that level of that height of water, actually height you are considering from here itself, from down, right? So the thing is, when time is very less, height of water will be more. As time is more, height of water will be less. In this case, when time is actually 4.2 seconds, in that case height of water you can see it is at this level, it is equal to near about 0.9 meter, right? And let us increase the time and see what happens to the height of water. You can see as time is approaching, by the same time height of water is also decreasing. At this moment you can see when 20.2 seconds, the height of water level has come down to 0.6 meter. Initially it was 1 meter, so height of water is coming down. As height of water is coming down, height of air is also increasing by the same way, right? Let us see this one again. You can see when it has come to 0, the height of water is actually, again you can see approximately 0.8 meter, right? Let us see the last part. At the extreme location, at the extreme bottom portion, we can see. Let us stop it here right now. So at 57 seconds, you can see the height of water is actually very less. It is in the range of 0.308 meter. So when height of water is 0.308 meter, in that case time will be 57 seconds. So at different times you can see what will be different heights of water, right? Let us close this one. Excluding this one, you can see something else, like let us change this Transient Explorer and you can see something else, right? So from results we can remove Transient Explorer. It's done. Now we'll see something else. Let us see load time moment diagram. It will show at different times what will be the height of water that can be viewed. It will not be quantified, it can be viewed only, right? You can see up to 60 seconds. You can see we have taken the time at 0.1 second onwards. We have saved the results with each 0.1 seconds. Suppose you want to see the distribution of this water and air at 47 seconds. Let us see at 47 seconds. So this is the level of water at 47 seconds. Exactly same way we can quantify that one also, that how much will be the height. That one can be viewed from the XY plot, right? So this is all about the first one. Now next case, what we will do? Next case we will change the boundary conditions. That means the direction of gravity will be changed. What will happen? From the bottom side, air will be entering and what will be coming down. So what we'll be doing in the next case, we will change the direction of gravity, right? Let us close this one, and for that, first of all, we need to clear these things, clear our cut plots, clear and hide. And in the next project number 3, we have changed the direction of gravity. Let us see that one also. From general settings, you can see that all the conditions are same, only you have changed the gravitational condition. Let us see that gravitational direction is actually plus 9.81 meter per second square in the upward direction. So with this boundary condition, you can see that water will be coming down. By the same time, air will be entering through this small opening, right? Let us load these results and you can see how it will be forming that mixture of water and air. So we can load the results from here. Results loaded. Now we can view the cut plots of volume fraction of water and air. Before that, we can insert the Transient Explorer also. Transient Explorer is on. Now we can view the cut plots of volume fraction of water or mass fraction of water. So insert cut plots, and you want to see mass fraction of water. Go and check. And we have taken this analysis for 5 seconds only. Let us run this Transient Explorer and see at what time what will be the volume fraction of water and air separately. That can be viewed very clearly, right? In this case, everything is same, only the difference is only the gravitation direction is only different. You can see at different times what will be the different volume fraction of water and air separately. Let us analyze this one. At the beginning moment, you can see the bottom part is open with a small hole. So as it is exposed to atmospheric air, due to gravitational action, water will come down. By the same time, air will go inside. So you can see air particles are going inside and it is being mixed with the air which was there at from the beginning inside this container. Let us play this again. Let us see the XY plot from here. Insert XY plot, and you want to see mass fraction of water. Let us select that line. Done. XY plot. Let us show that this is the XY plot. It is actually not linear in nature. You can see some kind of like ups and downs are there, right? You can see some kind of ups and downs are there in the curve. We can see it again. So with the boundary conditions change, little bit of change, you can see a lot of difference in the phenomenon of mixing of water and air. It is a heterogeneous mixture inside the container, right? Okay, so with this one we will conclude our today's analysis. It is a very simple analysis of a free surface technique. In this case, we have done heterogeneous fluid mixing of water and air inside a container with 2 different boundary conditions, right? Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.